Okay, here we are looking at Clostridium perfringens. That's cool. Clostridium perfringens is fascinating and horrible, but that's not why we are here. We're here to figure out how could we, in a more useful way, graph these numbers. And what we're going to look at is a semi-logarithmic scale, or semi-logarithmic graph. It's on the next slide, it's going to be a semi-logarithmic graph. So we're going to see a difference in the y-axis. The x-axis is going to be the same. That's why it is semi-logarithmic, because one axis is logarithmic. So here it is, and it looks odd. This is the same data set that I showed you here, where I asked you to try to figure out the value at that point, and where you couldn't with any real precision unless you looked at the little overlay that tells you the actual value. It's really not that important. So remember, this is so I asked you, tell me what's the value at that point, just as an exercise to see that you can't come up with a very precise estimate. But if we instead put the data on a semi-logarithmic graph, now, even though you might not immediately be able to use this graph, what you could see is that the numbers aren't all smashed at the bottom, and they don't go off the scale either. So what this is showing you is the same growth over several orders of magnitude. The highest point up here is roughly 500,000, and the lowest point is 2,000. And that's what the numbers were here. Oh, wait, 500,000. Oh, there was another point. There was another point I missed. So there's a point that I didn't graph here. So on this graph, we're seeing the same data. We're missing one point because I wanted to limit how much of it we had to look at. But all the numbers on this left side at the early times are the same. So I want to walk you through how to use a semi-log graph, semi-logarithmic graph. You notice this odd pattern of the lines. They don't, they're not evenly spaced the way what we call arithmetic graph, like this one. They're not, like this has evenly spaced lines, and here you go up by the same number each time. You're always going up by 200,000, another 200,000, another 200,000. Here, you're not doing that. If we break down these scientific notation numbers, what we'll see is that 10 to the third power is 1,000. 1 times 10 to the fourth power is 10,000. 1 times 10 to the fifth power is 100,000, and 1 times 10 to the sixth power is 1,000,000. So we can unpack that, and you can skip over this if you're really confident with your powers of 10 and everything. But I just want to show you, we have 1.0 times 10 to the third power. Well, what do we do with that? First of all, this is in scientific notation. We have an integer with a decimal point and maybe another number after it, but definitely we start with one integer. So one digit and then a decimal point after it times some power of 10. So if we want to convert this to a number that we recognize, what we can think about is that we are just going to multiply these together. But what is this part? What is this 10 to the third power? Well, that is a 1 with 3 zeros, or 1,000. So this number is 1.0 times 1,000. And 1.0 times anything is itself, so it is just 1,000. That's how you're supposed to read. That's how you're supposed to read this graph. This is supposed to be 1,000, and then up here, 10 to the fourth power, we have 1.0 times 10 to the fourth power, and again, we multiply 1 by something. What 1 times this is just this, so we have 10 to the fourth power, and that is just a 1 with 4 zeros, or 10,000. And before we move on, if this didn't make sense to you, if you're really not familiar with these powers of 10, what I would recommend doing is searching on YouTube or wherever you search for things you search for Khan Academy, what am I doing? What am I doing? For Khan Academy powers of 10. So Khan Academy has actual math teachers who know how to teach math, and all I know how to do is review math. So if you need a math teacher to help you, go check that out. There are several videos related to powers of 10. If you watch several of them, it will get you up to speed just fine. Put that to memory, that 10 to the third power is about 1,000, 10 to the fourth is 10,000, 10 to the fifth is 100,000. And let's look again at how this graph works. So instead of going up by a certain number, we're going up by a multiple. So instead of adding 200,000 like we did here, we're multiplying by 10. We're multiplying by 10. We're multiplying by 10. We're going up from 1,000 to 10,000 to 100,000 to 1,000,000, which is a million. So every time we go up the same distance, we multiply on this kind of graph. That's how it's set up, and that's why the lines are spaced the way they are. That makes it work out that a certain distance up is a certain multiple. So, and that's why an exponential curve becomes a straight line on this kind of graph. So let's magnify this, and let's look at some of these smaller lines and what they are, and we'll figure out how to do this counting. So we start at the bottom. Always start at the bottom. Find a labeled bar, like 1 times 10 to the third power. So that's 1 times 10 to the third power, and the first small line up above it, when we make that big jump, that's going to be 2 times 10 to the third power. And when we go up again, that's going to be 3 times this same power. And then 4 times this power, 5 times this power. So how's about pause the video and think about, what is 2 times 10 to the third power? What is 3 times 10 to the third power? Go ahead. So 2 times 10 to the third power is 2,000. 3 times 10 to the third power is 3,000. So we're going from 1,000 to 2,000, 3,000, 4,000, 5,000, 6,000. So here we are going up by 1,000 each time, but the distance we go up gets smaller and smaller and smaller and smaller. And I'll show you why that is in a little bit. So here we're going up by 1,000 each time. 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, all the way up to 9,000 and then 10,000. And here, if we were to keep going, 11,000 would be just about here, at 12,000, and they would just get closer and closer and closer. Instead, we skip all those, and we start now counting by 10,000. So we go 10,000. 20,000, 30,000, 40,000, 50,000, all the way up to 90,000, 100,000. And that's what 10 to the fifth power is. So if we go back here, we start at 1,000, 2,000, 3,000, 4,000, all the way up to 9,000, 10,000. And again, if we kept going, 11, 12, we would just be squashing those lines here. Instead, we start counting by 10,000. 10,000, 20,000, 30,000, 40,000, all the way up to 90,000, 100,000. We could do 110,000, 120,000. They'd be squashed here, but instead we skip them and we start counting by 100,000. 100,000, 200,000, 300,000, 400,000, all the way up to 900,000, and then 1,000,000. So part of why this is useful is that to go up a certain distance is to go up by a certain multiple. So check this out. You will have to do this. You will have to kind of measure informally the distance from 1 to 2, and you'll see it's the same distance from 2 to 4. So if we double a number, we go up by this distance, whether it's from 1 to 2, or whether it's from 2 to 4, or whether it's from 4 to 8, or from 8 to 1.6. So doubling always goes up by the same distance. If we go up by a multiple of 3, we go from here to here, from 1 to 3, and that's the same from 3 to 9, and from 9 to 2.7, or to 27. That's how this is supposed to work. And to go up by a multiple of 10, we go up by one of these big lines. So there you have it. That's what semilog graphing is supposed to do. So now pause the video, figure out which point is closest to 6 times 10 to the 4th power. And what you will find is that the answer to this is on the last slide of the Lecture 2 slides. So work it out, figure it out, go find it, and remember, we're counting down here. Each time we go up, we're counting by 10 to the 3rd power, and then in this middle rank, we're counting by 10 to the 4th power, and then this top rank, we're counting by 10 to the 5th power. All right, so that's enough of semi-log graphing. We'll move on to other things in the next video.